Hello everyone, we are Lia Conlin, Cathryn Caldwell, and Nhat Phan. Today we'll present calorimetry. So what is calorimetry? Calorimetry is a process of measuring the state variables of a body. The purpose of this process is to derive the heat transfer associated with changes of the body states due to chemical reactions, physical changes, and phases transitions under specified constraints. Calorimetry is performed by calorimeter. There are some different types of it. In our experiment, we use coffee cup calorimeter, which is considered as constant pressure calorimeter. This is an example of it, and Lia will show how to make it later. Before starting the experiment, I want to review some related concepts. First is system. System is quantity of matter or a region in space chosen for study. We have closed or isolated system and open system. Surroundings is the mass or region outside the system. They are separated by real or imaginary surface called boundary. In this experiment, the coffee cup calorimeter is considered as an isolated system. Secondly, I want to review equilibrium, which is a state of balance. There are 4 types: thermal, mechanical, phases, and chemical equilibrium. In this experiment, we cared about thermal equilibrium. Next concept is the laws of thermodynamics. Zeroth law of thermodynamics states that if 2 bodies are in thermal equilibrium with the third one, they are also equilibrium with each other. And if the third body is replaced by a thermometer, the zeroth law could be rephrased that the 2 bodies are in thermal equilibrium with if both have the same temperature reading, even if they are not in contact. The first law of thermodynamics states that the total energy of an isolated system is constant, and energy can be transformed from one to another forms but cannot be created nor destroyed. The second law of thermodynamics states that the total entropy of an isolated system can never decrease over time and is constant if and only if all processes are reversible. Isolated systems spontaneously evolve towards thermodynamic equilibrium with which the state with maximum entropy. Next, I have phase diagrams of water, the triple point where solid, liquid, and vapor phases coexist in equilibrium. The critical point is the end point of a phase equilibrium curve, and the liquid vapor critical point is the most prominent. There are 2 forms of thermal energy, latent energy and sensible energy. Latent energy is heat flow occurring at constant temperature. Sensible energy is heat flow accompanied by temperature change within a phase. So, in this diagram, sensible energy exists in state 1, 3, and 5, and latent energy exists in state 2 and 4.
First, we made a coffee cup calorimeter, which we'll be using as an insulated container for our isolated system. The calorimeter consists of 2 nested styrofoam cups and a styrofoam lid. We know styrofoam is a good insulator because it has a low thermal conductivity, which means it transfers heat poorly. So if we work quickly, we can perform our experiment with minimal thermal energy escaping from the system. We punched 1 hole in the side of the lid for our thermometer and another one through the center for our stirrer, which we made out of a few pipe cleaners. Next, we weighed out a small handful of metal screws. These are from the bottom of my tool bag, so I have no idea what their exact composition is, but they're probably made of steel. We held the screws in boiling water for a few minutes to let the metal rise to 100 degrees Celsius. Notice that we held them up to prevent them from touching the bottom of the pan, which would have made them hotter than 100 degrees. Finally, we filled the calorimeter with a bit of room temperature water and dropped the boiled screws in. We put the lid on and stirred the contents of the cup until the temperature reading stopped changing, indicating that the water and the screws had reached thermal equilibrium. We repeated the experiment with a smaller amount of water, hoping to see a higher final temperature. Our next experiment was pretty much the same as the first, but with hot water and ice instead of lukewarm water and hot metal. We poured boiling water into our calorimeter and then added a couple ice cubes. Then we put the lid on the container and stirred until the system reached thermal equilibrium. We repeated this experiment as well.
Earlier we discussed system and surroundings, and now we will define those for each experiment. In the first experiment, we define the system as the screws and water. In the second experiment, the system is defined as the ice and water. In both experiments, the boundary is the cup, and the surroundings are everything outside the cup. As mentioned earlier, this is an isolated system because there is no mass transfer or energy transfer. We assume there is no heat transfer because styrofoam has a low thermal conductivity. We will be solving for the specific heat capacity of the screws in experiment 1 and the ice in experiment 2. Specific heat capacity is the heat required to raise the temperature of the unit mass of a given substance by a given amount, which is usually 1 degree. In this experiment, specific heat capacity is the heat in kilojoules required to raise 1 kilogram of the substance by 1 degree Celsius. We will be using an energy balance on a closed system to get our equation to solve for specific heat capacity. We can simplify the equation by eliminating terms. Since the system is not accelerating, kinetic energy is 0. The system is not rising or falling, so potential energy is 0. Since we are assuming that the system is adiabatic, meaning that it is exchanging no heat with its surroundings, heat is 0. Finally, there are no moving parts, electrical currents, or any forms of boundary work, so work is 0. Now everything has been canceled out except internal energy. In experiment 1, there is internal energy in the form of sensible energy. So we plug in the equation for sensible energy, which is mass times specific heat capacity times the change in temperature for both the screws and the water. We will do the exact same thing for experiment 2 with the ice and water. The only difference is that in experiment 2, there is a phase change when the ice melts, so we have to add latent energy to the internal energy of the ice. Here is our experimental data for trial 1 and 2 of experiment 1. We plugged in the values from the previous slide into our equation and got that the specific heat capacity of the screws was 0.48 kilojoules per kilograms times degrees Celsius. We repeated this calculation for trial 2 and got a specific heat capacity of 0.39. Here is our experimental data for trial 1 and 2 of experiment 2. We plugged in the values from the previous slide and into our equation, this time taking latent energy into account for the ice, and got that the specific heat capacity of the ice was 1.79. We repeated this calculation for trial 2 and got a specific heat capacity of 4.62. In summary, here are the results of experiment 1 and 2. Although the exact composition of the screws is unknown, it looks like the values we solved for are close to the specific heat capacity of steel, which is 0.466. In experiment 2, the values from trial 1 and 2 differ significantly, most likely due to experimental error. Out of the two trials, trial 1 was the closest to the actual specific heat capacity of ice, which is 2.1.